it will come. So some brief discussions or a kind of an introductory thing for SEQuERE. It consists of a group of 4 faculty members, which includes the director, Professor Bhanu Das, who is also present, Professor Bhupen Dev, Dr. Prasanna, who is the administrator, and myself. My name is Devashish Mukherjee. We have 2 visiting faculty members, and our speaker, Dr. Sugisaki of the Osaka City University, is one of them, and Dr. Tapan Mishra of IIT Guwahati. We have 1 scientific officer, 3 postdoctoral fellows, 1 computational research fellow who is also present, 1 visiting scientist, 1 visiting doctoral researcher who is also present and helping us, and 2 internship students. There is an international scientific advisory board for SEQuERE consisting of Professor Arthur Eckert, Professor Yasunebo Nakamura, Professor Kenji Omori, and Professor Hartmut Hefner. I just briefly indicate that we have activity both in experiments and in theory, and experimental activity is one of the most vital activity here, and theory group would be making use of theories and models to undertake quantum computing procedures. Some activity of the theory group is working on quantum chemistry using quantum computers or simulators. And this is a research activity widely regarded as a major emerging field in quantum sciences and technologies, as you know. We have researches in several areas, which includes quantum many-body method, and there are several methods like that. And we want to get engaged in probing physics beyond the standard model of elementary particle, then looking into quantum computing efficacies of quantum chemical methods by developing a suite of many-body methods, either for studying precision spectroscopy or for studying potential energy surfaces of real chemistry, that is bond breaking and bond making. And also there is an attempt to go beyond the atomic and molecular science, delving into other prominent areas like quantum sciences and technology, like climate modeling and quantum information. The experimental group actually consists of 2 platforms where the 2 major activities are undertaken. One group actually is implementing a quantum computer using superconducting qubits based on Josephson junction circuits. And to enhance the coherence time of qubit, it will investigate decoherence effects by using various techniques and aspects of material science, such as surface and interface effects, etc., which is needed for fabrication of the Josephson junction. And it also plans to explore Majorana bound states in solid-state systems. And there is a special consultant for this activity, Dr. Vijay Raghavan of Tata Institute of Fundamental Research. The other group centers around a research plan with 3 goals: to develop a full stack of any ISQ, the NISQ quantum computer-based trap time exploration, and to look at quantum advantages using the machine with high fidelity, and to develop distributed computing by faster interconnect. And Dr. Manush Mukherjee, who also probably is present, of CQT Singapore, who is an advisor also of SEQuERE, will initiate this project. From August 2021, that is middle of this year, SEQuERE has entered into an MOU with the IIT Tirupati for a joint pre- and postdoctoral activity. There will be PhD courses offered by us and which can be taken by IIT Tirupati, and PhD degrees for students working in our institute will be offered the degree by IIT Tirupati from 2022. We have started some research activity of various types, as a matter of fact, and the courses are getting developed for the PhD courses, and this will really grow much further. There are activities at the postdoctoral level too, and there are several postdocs, as I indicated. I would probably just close the activity profile by just emphasizing that we expect to grow both in depth and in the scope of reach of our research as time progresses. So now we come to introducing Dr. Sugisaki, our guest for the meeting today. Dr. Sugisaki holds the special appointment lectureship in Osaka City University in Japan, and he's also concurrently a Presto Grant awardee of the Japan Science and Technology Agency. He also, as I emphasized, a visiting associate professor of our own CQuERE in TCG CREST. And he is collaborating with Professor Bhanu Das, Dr. Prasanna, both from our center, and Professor Vijay Sahu of the PRL Ahmedabad, and actually had been doing this for quite some time. I just indicate some major current research interests of Dr. Sugisaki. These are in the theoretical understanding of the molecular and electronic structures of open shell organic, inorganic molecules and radicals. And I particularly mention his strong involvement in the development of quantum algorithms for quantum chemical calculations of strongly correlated systems like open shell molecules and radicals. Theoretical methods for spin-spin and spin-orbit contributions for zero-field splitting tensors and other spin Hamiltonian parameters. Theoretical studies of molecular and electronic structures of reactive intermediates, and unusual molecules such as carbines, nitrines, and radicals, and a host of other various interdisciplinary fields conflating all this. And that really opens up a lot of possibility. We have read and discussed with great interest his recent multi-reference unitary coupled cluster-based quantum algorithm for bond dissociation in beryllium hydride, which appears in the archive. This is a singularly interesting paper, has remarkable potential, as we feel, and along with this, he has been involved in other quantum algorithm researches, and we may think of several. I just mentioned only a few. Preparation of the spin symmetry adapted configuration state wave function. These are used as initial guess and to be used concurrently with quantum phase estimation based full CI. Essentially, this is the general strategy. He also developed a new quantum circuit to prepare the CSFs on quantum computers with a constant circuit depth, and that is very important. He also proposed a method to prepare multi-configuration wave function having sufficiently large overlap with the full CI root of the ground state by using diradical characters, but this time without performing the time-consuming post-34 calculation. That promises to be of great importance. He also developed theoretical methods to simulate time evolution of wave function under the S-square operator on quantum computer. So it essentially enables one to determine spin quantum number S of arbitrary wave function by using quantum phase estimation. And this also enables one to use a probabilistic spin annihilator, so keeping the spin eigenfunction nature of a function as it evolves. Dr. Sugisaki has written a book in Japanese on quantum chemical calculations on quantum computers. This is the first textbook in the field written in Japanese, and this is published by Kodansha Limited, which came out in December 2020. He had also been organized in the recent past international workshops on quantum chemical calculations on quantum computers every year, which has now been temporarily suspended due to the COVID-19 spread. Among the accolades he has received, I may particularly mention the Young Investigator Award of the Society of Electron Spin Science and Technology, SEST, in 2019. The series of lectures that he intends to give will be beamed via both the microwave teams of the TCG CREST and by the YouTube. Those attending the former will be able to ask questions directly after the end of the talk, roughly spanning an hour or so in duration. Those attending the latter will be able to ask, unfortunately, questions only at the end of the talk, but writing them on the chat mode, which will be picked up by Dr. Prasanna, who is the administrator of the meeting. We profusely apologize to the guests for this inconvenience. I hope it would not be repeated in the past, in the present, or in the future. But this time, I don't think we can do much about it. It's now my pleasant duty to request Dr. Sugisaki to kindly deliver his first talk in the series. And from now on, Dr. Prasanna will take over as the administrator of the meeting. Dr. Sugisaki.
Thank you very much for the kind introduction. So welcome to the lecture series of the quantum chemistry on quantum computers, which is organized by the Quantum Center of Quantum Engineering Research and Education in India. And as already introduced by Professor Mukherjee, this lecture series includes 8 lectures. And today is the first lecture. I'm going to tell us the general introduction of the quantum computers. And before starting my lecture, let me introduce by myself. But already Professor Mukherjee introduced very in detail, so maybe I can skip this slide. But anyway, I'm Kenji Sugisaki from Osaka City University. I'm currently in the special appointment lecturer position in Osaka City University, and also in the position of visiting associate professor in CQERE, the center. Mainly, I was working on the quantum chemical calculation of optical molecules, but since 2011, I started to study the quantum algorithm for quantum chemistry. I wrote the book on the title is Introduction to Quantum Chemical Calculation on Quantum Computers. I'm sorry, but this is written in Japanese and currently no English translation, but anyway. And this lecture series includes 8 themes, starting from the introduction of quantum computers. And next, I would like to introduce some quantum algorithm or mechanism how quantum computers calculate the problem. And then I will introduce the quantum phase estimation algorithm, which one of the most famous algorithms used in quantum chemistry. After that, I will introduce how to map the wave functions on quantum computers and how to construct the quantum circuits for quantum chemistry problems. And then I will introduce some variation quantum algorithms. This is the quantum and classical hybrid algorithms, which is available for currently available noisy quantum devices. And then I will introduce some adiabatic quantum algorithms, including adiabatic state preparations and quantum annealing. And then I will introduce some computational complexity. And finally, I will tell about the techniques to resolve, the qubit or quantum gate and error reductions. How to reduce the errors, or how to reduce the number of qubits or quantum gates to perform some quantum chemistry problems. I think the most famous statement on the beginning of quantum computer was given by Richard Feynman in his seminar talk in 1981 in MIT. He discussed some particle of quantum particle. Let's think about one quantum particle. Simulating one quantum particle is very easy, even on classical computer. But if the number of particles become very large, so the x1, x2, and xr, where r is the number of particles, and if the number of particles become very large, it cannot be simulated with a normal computer or classical computer because it has too many variables. But he proposed that he pointed out that this kind of problem can be solved by using a computer with quantum mechanical elements which obey quantum mechanical laws, namely the quantum computer. But in his talk, he didn't say anything about some quantum acceleration by using quantum superposition. So the true beginning of quantum computer can be given by Professor Deutsch in 1985. In 1985, he proposed this paper, quantum theory, the Turing principles, on the universal quantum computer. In this paper, he introduced the quantum Turing machine for quantum computers and how to perform the computation. And his idea was born from the conversation with Charles Bennett, IBM. That day, in 1980, and this was taken from the New Yorker magazine. According to this, in 1980, he attended some international conference on the computation complexity, and he in computation complexity, sorry, they discussed how many the scaling of the computation cost. I mean, how many operations are needed to perform some certain problems, and the scaling of the computation cost against the problem size. But he thought such operation, the number of operations should depend on the elementary operations. And he asked such question to Charles Bennett, but Charles Bennett answered that the operation cannot be arbitrary, but it's defined from nature. Professor Deutsch thought about the okay, so in that case, the quantum mechanical principle can be used as a source of the elementary computation. And that is the start of the quantum computer. What is a quantum computer? If I define the quantum computer in one sentence, quantum computer is a computer that operates according to quantum mechanical principles. And the biggest difference from the conventional or classical computer is quantum computer use quantum bits or qubits as a minimum unit of information. I will introduce the qubit later. And some problems, the computation cost increase exponentially against the problem size on classical computers. can be solved with polynomial cost by using quantum computing. And 2 years ago, a Google group reported the quantum supremacy using the superconducting quantum circuit processor. Looking to this paper, they performed some kind of simulation on 53-qubit quantum computer SCAMO in 200 seconds. If the same computation will performed on supercomputers or classical computers, they estimated the required time is 10,000 years. So this is the first example of the quantum acceleration. But unfortunately, there are many misconceptions or hypes in quantum computing. Before starting talking about the detail of quantum computing, because I will go to some misconceptions. One big misconception is that quantum computer can solve any problem faster than the classical computer. Fortunately, this is not. Not any problem can be accelerated to solve by using quantum computers. So it means that a problem that can be accelerated by quantum computers is very limited. Another misconception is quantum computer can solve particular problem faster than the classical computer. Unfortunately, this is still not exact. Why? Because exponential speed up is guaranteed for some quantum algorithms, such as prime factorization or hidden subgroup problems. But this statement is only for the scaling of the computational cost against the problem size. So it means if we say exponential speed up, we think about something like this. Assume that n is the size of problem, and to solve the some problem of size n takes order of the a to the power of n, a to the nth power on classical computer. So it means that the computational cost increased exponentially against the problem size on classical computer. But for some problems, there are no quantum algorithms to solve the same problem on quantum computer in polynomial scaling. So maybe exponential speed up is not the exact word, but it means the exponential improvement of the computational cost scaling against a problem size n. So even if the quantum algorithm, which can be accelerated exponentially, are known, it say nothing about the what size of n, the size of n, where the quantum computer can calculate faster than the classical computer. So the speed up is of course depends on the size of n, and also the computation time for elementary operations. So that's why this statement is still not exact. Another misconception is exponential improvement of the computational cost scaling against the system size. I mean, the number of electrons or base set is possible by using quantum computer for quantum chemistry problems. Again, this is a misconception. I mean, the exponential improvement can be achieved or not. It depends on the algorithm being used. I will going to talk about the two major algorithms. I mean the quantum phase estimation and variation quantum eigensolver. QPE, I mean the quantum phase estimation. It can obtain eigenfunction, eigenvalue of the Hamiltonian with polynomial cost. Classical computer, it corresponds to the full CI calculation. So it takes exponential time or cost against the molecular size. But variation quantum eigensolver, this approach can obtain the expectation value of the approximate wave function with probably polynomial cost. And because this VQE can obtain the expectation value of the approximate wave function, the calculation of such computation can be done in polynomial time on classical computer as well. We are thinking about the couple cluster method. If the computation cost scale about the n to the 6th power, where the n is the number of basis set. So it's already polynomial. And on quantum computer, there's also polynomial. So using quantum computer is not a sufficient or necessary condition of the quantum observation. It depends on the algorithm. This is a very important point. So let me introduce the quantum bit or qubit. On classical computers, we use the bit. Bit can be either 1 or 0 state, or on or off state, meaning unit of information. But quantum bit or qubit can be arbitrary superposition of 0 and 1 state. So quantum state can be written as shown here for 2-level systems. So for 2-level systems, 0 can be the ground state and 1 can be the excited state. And here, C0 and C1 are complex numbers satisfying the normalization conditions. So the quantum state of qubit can be represented by using a box sphere, as shown here. And quantum state of 1 bit can be the only sphere of this unique ball sphere. And the quantum state can be represented by using a theta and phi, as shown here. And theta and phi are defined here. Because quantum bit can be in a superposition state, but if we measure the quantum state, let us think about the quantum state phi is 0.6 times plus 0 and get 0 and 0.8 get 1. And if the measurement is performed, the quantum state will project to the eigenstate of the measurement operator. I mean, in this case, the 0 or 1 state, with the probability depending on the square of the question. So when we measure the qubit to bring out the results, the quantum superposition is destroyed. So for this reason, if we can generate the, for example, 0.64 state by using cluster bit, it's still not equal to the quantum bit state, this quantum state, because the measurement will just give the 0 or 1 state. And quantum state can be entangled, in which the measurement of one qubit affects the quantum state of the other qubit. And let us think about the quantum state shown here, 2 qubit states with the equal probability of 0, and 1 and 1, 0 and 1, 1 states. This is unentangled state. And let us think about the situation just measuring the first qubit and then measure the second qubit. And if the measurement outcome of the first qubit is 0 state, the quantum state after the measurement of first qubit is just a linear combination of 0, 0 and 0, 1 states. And the measurement outcome of the second qubit should be 0 or 1 with 50-50 or equal probability. Again, the situation is the same for if the measurement outcome of the first qubit is 1 state. Again, if the first qubit measurement outcome of the first qubit is 1 state, and measurement outcome of the second qubit should be a equal probability of 0 and 1 state. But the situation will be different for entangled state. Let us think about the quantum superposition of 0, 0 and 1, 1 state. And if we measure the first qubit and obtain the 0 state, it means the quantum state after the measurement of the first qubit is projected to the 0, 0 state. So in this case, the measurement outcome of the second qubit is always 0 state. Again, if the measurement outcome of the first qubit is 1 state, in this case, the quantum state is projected to the 1, 1 state after the measurement of the first qubit. So in this case, the measurement of outcome of the second qubit is always 1 state. This entangled state is one of the features of the qubit. And there are many types of qubits, I mean the physical qubit systems. And this cartoon was taken from the Economic Journal in 2015. And this is the quantum computing race. And as you can see, this is the superconductors, so superconducting circuits. And this is the photons, and this is the calcium ions, so it means the type ion systems. Of course, there are some. These three are not all the architecture. I mean, there are several another candidates for qubits, such as nuclear and electron spins, and semiconductors, and ion fermion, and so on. But let me introduce, explain the qubit by using electron spin. As you know, the electron spin is the quantum magnet. But let us think about the crystal magnet, like a compass. If you put the compass on your table, it stops directing north and south. But for electron spins, I mean the quantum magnets, it doesn't stop, because if it stopped, it violates the Heisenberg principle. So it causes some precisions and along the external magnetic field. And if the quantum states can be the up spin and down spin, or ms equal plus 1/2 and minus 1/2. But the magnetic moment is directly to the external magnetic field direction, and we can assign this moment as the quantum state shown here. If we apply pulse microwave, we can manipulate the spins to change the quantum state. And the computation on quantum computer can be performed like this. Starting from some initial state, usually the social state, and then perform some quantum operation. This should be unique operation, which cause some changes of the quantum state and finally measure the quantum state. So the what kind of quantum operation should be applied? It depends on the what kind of the algorithm we want to apply. But there are several elementary quantum operations. I mean the quantum gate. So let me introduce some quantum gate operation. Let us think about the quantum state directed to zero state. I mean plus the position direction. I mean the quantum state in the zero state. And if we apply 180 rotation around the axis that bisects Z and X axis in direction, applying this quantum gate can change the quantum state direct to Z axis to X axis. And this is a well-known gate as a known gate as an Agamal gate. And Agamal gate, usually Agamal gate is represented as H, not HD, but in my presentation, I often use the HD because pure H is sometimes represent the Hamiltonian. So as you can see, this kind of C to X state transformation can be done by applying the 90-degree rotation around the y-axis. But as you can see, if this is 180 rotation around this axis, applying Agamal gate twice can generate the original state, can reproduce original state. And the action of the quantum gate can be calculated by using a matrix algebra. And this is a matrix representation for the Agamal gate. Let us think about the quantum state, which is a superposition of 0 and 1 state as shown here. The quantum state after the application of the Agamal gate can be calculated as shown here. This slide shows several quantum gates which can be used as elemental operations. I will introduce these quantum gates later. I mean for the power gate here is the simplest one, I think. The representation is 1, 0, 0, minus 1 and diagonal form. So it means the power Z, the quantum state on the Z axis plus, I mean the 0 state or 1 state are the eigenfunction of the power Z operator, with the eigenvalue either 1 or minus 1. Similarly, the power X and Y, for pi X and Y, the quantum state on the X and Y axis are eigenfunction of the power X and Y operators, with the eigenvalue either 1 or minus 1. Okay. And we can calculate the action of the power x, for example, to the eigenstate of the, the plus x state can generate the original function state. Applying the power x operator to the minus state will generate the original state with minus sign. So the eigenvalue of the power x for the minus state is -1. And similarly, the same thing can be done for the power y state. And this is the rotation gauge and phase shift gauge. This Rx and Ry and R3 are rotation gauge along x, y, and z axis, respectively. And this P is a phase shift gauge. It will shift the quantum state, the phase of the quantum state, if the qubit is in one state. If the qubit in zero state, they apply nothing. The identity operator here. Apply the phase shift on the minus for one state. As you can see, the phase difference between 0 and 1 state after the application on RC and P theta is the same. And the only global phase is different between this RC and P gauge. As you can see, if the P theta gauge is applied with theta is equal pi, it means that the multiplication becomes 1, 0, 0, -1. So this is a power Z gauge. If we apply P gauge with theta is pi over 2, it's sometimes called as a S gauge. And pi over 4 is a T gauge. And this is a 2-qubit gauge. And the famous 2-qubit gauge are Single and Schwab gauge. The single gauge will apply a knock operation to the target qubit if and only if the control qubit is in the one state. And here, in the circuit symbol, this small dot represents the control qubit, and this circle represents the target qubit. If the control qubit is in zero state, it applies nothing to the target qubit. But if the control qubit is in one state, it applies the knock operation. So signal is the control knock operation. Another very famous quantum gate, 2-qubit gate is swap operation. And this swap operation just exchange quantum state of 2 qubits of J and K, for example. So applying swap gate to QJ, QK state will generate the QK, QJ state. And usually, in the control knock gate, this cross circle is used to represent the control qubit. But sometimes open circle notation is used to represent the single gate. But in this case, apply a knock operation if and only if the control qubit is in the zero state. The cross circle means the control is one state, apply knock operation. But in open circle representation, they apply a knock operation to the target qubit if the qubit is zero state. So this open circle representation of single gate can be rewritten as shown here. I'm applying knock operation to the control qubit and apply a single gate and again apply a knock operation to the control qubit. But this open circle location is very general, but unfortunately, it's not familiar not so famous. So if you use this open circle notation, I recommend to say some words on the definition of the open circle notation. And also, you can define a 2-qubit gate by adding a control qubit, like control RC gate, as shown here. Applying, in this case, applying the RC gate to the target qubit, if and only if the control qubit is the one state. These 3-qubit gates, and 3-qubit gates are very sparse, so I mark the non-zero term as red. And this is not gate, it's a control knock operation, sometimes called as a Toffoli gate. You can easily understand the action of the this system of gate, applying the knock operation. If these two control qubits are in the one state, so applying, so if the two control qubit is 0 or 1 or 1 0 states, it's applying nothing. And if the control qubit is 1 and 1, in that case, apply a knock operation. Another famous 3-qubit gate is control swap gate, also known as a Ferguson gate. And in this gate, apply a swap operation if and only if the control qubit is one state. And the matrix becomes something like this. This by 4 matrix is for the control qubit is the one 0 state. So this is just a unit, just a diagonal operator. So apply nothing, and this 4x4 matrix is the action on these two qubits if the control qubit is one state, and this structure is just the same as this swap operation. Another gate is the Dodge gate. In this case, the Dodge gate apply some rotation to the target qubit. If two control qubit is in the one state. And by combining these quantum gates, we can generate the maximum entangled states in 2-qubit systems, known as the base state. Actually, the base state can be generated by applying or combining the Agama and power X and single gate. And this is an example of the base state generation. And this is a screenshot of the IBM Q, and you can easily check how to perform the computation on IBM Q. I mean, and this quantum circuit consists of only 2 quantum gates. I mean, Agama and single gate. Sorry, Agama and single gate. And the quantum state after applying this quantum gate can be calculated as shown here. First, we apply an Agama gate to the first qubit to generate the quantum state is initialized to the 0 state. And applying the Agama gate to the first qubit will generate the superposition of 0 and 1 state, so 0 plus 1 0 state. And then apply a single gate to with the first Q0 first qubit as a control and the second qubit as a target. In this case, the single operation will change the second qubit state from 0 to 1 if the control qubit is in one state. So applying this quantum gate, we can generate the 0 0 plus 1 1 state. Okay, so because this quantum, by applying this quantum circuit, we can generate this case. So I would like to first ask a question: how to construct the quantum circuit to generate other field-based case? I mean, equal superposition of the 1 plus 1 zero case and 0 1 minus 1 zero case and 0 0 minus 1 1 case. From the quantum state inside to the zero state using Alama, power x and signal k. The answer is shown here. This is the quantum circuit for generate. This is the quantum circuit to generate the superposition of 0 0 plus 1 1 state. But if we add another knock operation to this factory, it can generate the superposition of 1 0 plus 0 1 states. For the preparation of 1 0 minus 1 0 1 minus 1 0 state, we can apply another knock operation from the beginning of the quantum circuit. It can generate the 0 state from the 0 state to generate the 1 0 state, and then apply a gamma gate to generate the 0 minus 1 state, apply signal gate to generate the 0 minus 1 1 state, and finally applying the another knock operation to generate the 1 0 minus 0 1 state. And 1 0 plus 0 1 state, so 0 minus 1 1 state can also be generated by removing the final knock operation shown here. But there are many other quantum circuits to generate the same base state. For example, this quantum state, this base state can be generated by applying a Argamal and Xenon and Pauli gate, as shown here. And there are, so basically we can construct the quantum circuit by combining these quantum gates. But so, how to construct the quantum circuit? There are universal quantum gate set. I mean, the universal quantum gate set means that any unit operation in the Hilbert space of n qubits can be decomposed by using universal quantum gate set, this quantum gate set. And there are several types of the universal quantum gate set. And one famous definition is arbitrary 1 qubit rotation gate and single gate. So this means that any unitary operation can be decomposed by using arbitrary 1 qubit rotation gate and single gate. Another definition of universal quantum gate set is Argamal and phase and signal and pi over A or T gate. Another definition is Deutsch gate. I think that this first definition is very famous, but sometimes this second definition is often used because the Gauguin near theorem states that the stabilizer circuit can be efficiently simulated on classical computers. And this stabilizer circuit includes some quantum gates from the Clifford group which include Agamal and phase data, and signal and power X1, A, and Z. In this second definition, Agamal and phase and signal gates are included in Clifford group. So this quantum gate can be simulated on classical computer efficiently. But inclusion of this key gate is very important to some advantage of quantum computer. So some papers discussing on the gate complexity. Sometimes they count the number of Agamal phase and signal gate and T gate. An important thing is the previously showed the base case generation. Base case generation can be done by applying Agamal and signal and probably X, Y, or Z gate. So it means base case generation can be efficiently simulated on classical computer. Base case are entangled gate, entangled state. So it means quantum entanglement is not the only the source of the quantum acceleration. Let's think about the quantum circuit as shown here. This quantum circuit consists of the two Agamal gates shown here, and two signal gates, and another signal gate, and then measure the quantum state. The quantum state before the measurement can be calculated as shown here, starting from the Agamal gate to the first qubit, which will generate the superposition on 0, and 1, 0 state, and then apply another Agamal gate to the second qubit, which generates the quantum state on here, and the signal gate will change the last qubit, quantum state of the last qubit. If the first qubit is in one state, so 1, 0 state will become the 1, 1 state, and 1, 1, 0 state become 1, 1, 1 state. Another signal gate will generate the superpositions. And finally, this signal operation will generate the will change the third qubit, quantum state of the third qubit from 0 to 1 or 1 to 0 if the first and second qubit are 1, 1 state. So the final quantum state is something like this. So if we measure the quantum state, this quantum state, the measured outcome should be equal probability of the 0, 0, 0, 0, 1, 1, 1, 0 state, and 1, 0, 0, 0, 1 state, and 1, 0, 1, sorry, 0, 1, 0, 1 state. And this is the output from the state vector simulator from IBM Q. And the measured outcome should be from right to left order. Qubit will align to right to left order. But if this is the result of the simulator, quantum circuit simulator, and if we apply the same quantum circuit to real quantum computer, and this is the result of the real quantum computer, this simulation was carried out using IBM Q manual, which is a 5-qubit system available from IBM Q. As you can see, the 60000 state and 1110 state, 1001 state, and 101 state have larger probability than the other quantum state, but the outcomes that was that doesn't appear from the numerical explanation. And you can check the real quantum circuit. I mean, the original quantum circuit is just 5 quantum gate, consists of 5 quantum gate, but the quantum circuit calculation on the real quantum computer is carried out by using these quantum gate. In this case, we need 42 quantum gate to execute this original 5 qubit gate system. Why? Because there are several reasons. And this is the brief overview of IBM manual. And this is the basic. As you can see, this is the basic gate. So basic gate means the quantum gate executable on this IBM manual system. It includes CX, means the control node operation, and identity, and RC, and square X, and X operation. So it means this, for example, this CC node operation is not directly applicable on IBM manual system. And also, this is the connectivity of the qubits. IBM Q, the 5 qubits are aligned linearly, and this keep represent the connectivity. So it means that 2 qubit operations are available. Only the 2 qubits linear adjacent 2 qubits. So it means the original this quantum circuit includes the single operation from 0 with the control qubit is 0 and target qubit is 3. But the 0 and 3 qubits are not directly connected. So we have to swap the quantum state to make the original good, for example, by swapping 2 and quantum state of 2 and 3, and then another swap operation between 1 and 2 to make the quantum state, the original 0 and 3 state are adjacent to each other. So that's why we need many qubits. Many quantum gates to execute this original 5 qubit gate. And also, as you can see, there are many noises. Actually, the quantum available device is very noisy, and the number of qubits is very small. And John Preskill defined the quantum available quantum devices as a NISQ device. NISQ is the noisy intermediate scale quantum device. Usually, it contains about 50 to 100 qubits. So this number of quantum bits is too small to implement quantum error question. I will explain the quantum error question in the next slide. And the number of executable coherent gates is at most 1,000 or something. So noise is very large, and also if the 1 qubit operation can be executed by, for example, 99% of fidelity, and if we apply a 1 qubit operation with 99% of fidelity, for example, 100 times or something, the error increases more and more. So it's very difficult to obtain reliable results from the NISQ device. So we need some error correction scheme. Actually, the classical bit is very robust against the noise. But because in classical bit, for example, in transistor, it can be, if the classical bit can be on if the voltage is higher than threshold, otherwise off. And noise, if there are noises, in the presence of noise, it can be very robust as long as the noise is very small compared to the noise as long as noise cannot exceed a threshold. And also noise errors will reset every time when the operation proceeds. However, the situation is very different from the classical computer. Actually, the quantum bit is very fragile against noise because different hit and phi mean the different quantum state. So if the quantum state fluctuates by a small fraction of theta over phi, it can be the different state. Error accumulates by proceeding operation. Also, because of the qubit is not completely separated from the environment, so quantum superposition can be destroyed by system environment interactions. This is also known as decoherence. So quantum bit is very fragile against the noise. So how to circumvent this problem? One simple idea is use multiple physical qubits to retain information of the one logical qubit. This is a basic idea of quantum error correction. Here I will represent the very simple 3-qubit big flip code to explain how the quantum error correction proceeds. This 3-qubit big flip code uses 3 physical qubits to represent one logical qubit and need another 2 qubits, auxiliary qubits, to detect and correct single big flip error. So the system, so the original quantum state, the logical qubit state, is mapped to the 3 qubit. So logical 0 state is now mapped to the 000 state. And logical 1 state is mapped to the physical 111 state. So the arbitrary superposition of 011 state can be written as shown here. 000 and 111 of superposition. And let us think about the situation when the 1 qubit flip occurs. Big flip occurs. This is a quantum circuit for the detection of the big flip error. We need 3 physical qubits for mapping, and we need another 2 qubits to detect the error. If we apply this quantum circuit, if no big flip error occurs, the quantum state before the error correction is something like this. Quantum state after the measurement is something like this. So if we measure this auxiliary qubit, 2 auxiliary qubits, if no big flip error occurs, the measurement outcome is always 0 state. If the big flip occurs to the first qubit, the quantum state in the input is something like this. Big flip occurs, so original 0 state will now be in the 1 state, and original 111 state is now in the 011 state. And if we apply this quantum circuit, the measurement, quantum state after the measurement is, before the measurement is something like this. So measurement outcome is always one state. If we apply the three qubit display code and measure the quantum ancillary quantum bit measurement outcome was one state, we can apply another knock operation to the first qubit to correct the error. If the second qubit flip occurs, the quantum state before the measurement is one something like this, and the measurement outcome is one cross state. So in this case, so we can say that if the measurement outcome is one cross state, it means the second qubit was flipped. So we apply a knock operation to the second qubit to correct the error. And similarly, if the third qubit flip occurs, the quantum state after the measurement is shown here. So the measurement outcome is always one state. So the measurement is 0, 1 state. We can apply a knock operation to the third qubit to correct the error. And of course, this flip code is applicable only the big flip errors. I mean that if the phase becomes somewhat rotated, for example, starting from 0, and 1, state, and some error cause some phase shift between 0, and 1, state could generate the, for example, 0, minus C1, 1, state. In this case, such phase shift cannot be detected and also corrected by using this big flip code. And also, if two qubit flip occurs, for example, starting from 0, state, and big flip occurs to this first and second qubit to generate 1, state. In that case, if we apply this big flip code, it will generate a 1, state. So this big flip code is applicable only for the correction of the 1 qubit flip. If 2 qubit flips, it doesn't work. So basically, if the physical qubit, the number of physical qubits could match the logical qubit, will increase the error correction become very robust. And also we can apply another error correction code, such as surface code or something. We can correct the phase shift error or something, or other errors. But basically, this idea of the quantum error correction is shown here. Applying meaning some ancillary physical qubit and ancillary qubit to detect the errors and correct the quantum state of the physical qubit by depending on the measurement outcome. So this is the fine. So this is the final of the today's talk. So next week is the next Thursday is the national holiday in India. So the next lecture will be given in the 2 weeks later. Thank you very much for your kind attention.
Many thanks, Dr. Sugisaki. I will request
thank you, Professor Sugisaki. Thank you, Professor Mukherjee, and thank you, Professor Sugisaki, for your very nice talk. And I thank you on the behalf of. So, if anyone has any questions on the Teams chat, then maybe we can take questions. Yeah. If not, then I can ask a question from the YouTube segment. So Dr. Dasgupta asks on the slides where you discuss RZ theta, RX theta, etc. on that.
This one?
Yes. So here he asks if P theta should be with respect to a unit vector.
Could be with respect to unit vector. Yes, basically yes. I mean the unit vector means that of course the quantum space is represented by a unit vector. So basically the applying the quantum state to be applied to the P sigma J is basically general. I mean it can be the quantum superposition or pure state. But anyway, the quantum state is represented by a unit vector as long as we consider the pure state. Because the quantum state, pure quantum state is represented as a point on this box sphere. So the quantum state can be represented. The norm of the quantum state is one unity.
Okay. Thank you for your answer. Are there any more questions from anyone? I'll just go back to YouTube to check if there are any queries from YouTube. Okay. So as of yet, there are no other questions. So should we wait for a minute or so, and then if there are no more questions, then
Yes, there's some time lag between the talk and YouTube stream. So
true. Yes, there is a question from Nishant. So he asks regarding quantum misconception. Can we achieve polynomial speed up if not exponential for molecular calculations?
yes, maybe. Also, I mean if we use the quantum phase estimation algorithm. Let me back to the slide somewhere. Yes. If we use the quantum phase estimation algorithm, this quantum phase estimation algorithm satisfies theoretically the exponential speed up is guaranteed. But in case of VQE, it depends on what the answers to generate the approximate wave function, basically. Because the computational cost of VQE, I will discuss the detail in the fourth lecture, I guess. But anyway, if we use, for example, unitary couple answers, the computational cost from the number of variables is something like the number of occupied orbital square times number of virtual orbital square. So it's something like n square or n cubic or something, where n is the number of bases. So this scaling affects the depth of the quantum circuit, and we need n to the third power of the measurement to obtain the energy expectation value. We need another cost on the optimization. So in that case, the unitary couple cluster, I think in the unitary couple cluster, computational cost scaling is something like n to the 7th power or something. So it is higher than the conventional couple cluster, because couple cluster single double is about the n to the 6th power. But if we use another answer, for example, Hardware exchange answer, in that case, the depth of the quantum circuit can be smaller than the unitary couple cluster. So in that case, the polynomial acceleration can be expected. So the situation is very different between QPE and VQE. If we use the quantum phase estimation, the exponential speed-up guarantee, as long as the good initial gateway function is applicable in polynomial time. But anyway, in case of VQE, it depends on the answers. So constructing good answers is very important to achieve the acceleration by using quantum computers.
Okay. Thank you very much for answering the question. If there are no more questions, then I'll again thank Professor Sugisaki for a very nice lecture.
Thank you very much.
Thank you, and thank you very much. Thank you. Okay. Thank you. I will disconnect the call.